Recording is started. Hi everyone, uh, Prakash here, and what I am going to do is I am going to start with the slideshow first. Uh, so we are on the part 2 of the quantum computer gates and circuits, and this is going to be the last session 11 for part 2 for the gates and circuits. So you know that we did the quantum computing fundamentals in the session 1 to 6. Session 7 I started, and 8 I partially participated. Then 9, 10, 11, 9, 10, 9 and 10 I gave it to Gokhale, who presented. Today I am trying to close it with the quantum circuits. Are you all able to hear me and see the slides? Can one of you comment? Any one of you? Okay, thank you. So you are listening as well, hearing all I'm saying. Okay. So with that, I'll move on. So this week we want to cover part 1 and part 2. Um, Professor Gokhale wants to cover part 2. He has a commitment. He is flying to Mysore for some Independence Day celebration. And it's in India, it is 15th August, I believe, so which is a Independence Day. So he told me, we conversed, and finally what I got is his slides, his whatever the IBM quiz kit portions I got. So I'm going to do that as well, part 1. So I will try to go through part theory, part what you call the practical lab part of it. So let me start with first no-cloning theorem. So remember that we had gone through some of the things. Now, the difference between me and Professor Gokhale has been that I have been following the logic of MS bit to LS bit. Yes, he did follow MS bit to LS bit, but IBM quiz kit deals in a LSB to MSB fashion for the qubits. And that causes some confusion. That's why I left Professor Gokhale to continue. Since he is not available, I'll have to go back to my seventh lesson, seventh session, and then start working through it to the direction in which he was going. So let me first clarify on no-cloning theorem. So if you look at a classical register, computer register, whether it's in memory, whether it is in the CPU registers, you can actually take it and copy it to any other place in another system. So if you have a system A, system B, I can copy the registers from system A to system B or system A to memory. In quantum, that copy business is not allowed. And as Professor Gokhale also mentioned to you, that if you have a buffer in algorithms, what we do is we take the uh, register, or we take the content, put it into a buffer, and then um, swap it. And that's how you do the copying and all. That is not practical. However, we assume that it is practical. Let's prove that it cannot be. So to do that, we have to assume two electrons. One is system A and system B. You remember we showed two electrons with a zero state, with circling zero state and one state. So same way we are taking two electrons, one in system A and one in system B. And then we say that system A is in a state which is represented ket psi as alpha 0, alpha ket 0 plus beta ket 1. Same may be said of second one also, but to start with, we'll assume that, so normally what happens, you have a register, you copy to a zero register, right? You have all zeros, then whatever bits you have, you copy it and it will become that. So if I have a 4-bit register with 1 1 0 0, and if I have another register 0 0 0 0, then if I copy, then it will become 1 1 0 0. Same way, what we do is we assume that there is a system A with a ket psi, which is nothing but a that is superposition of ket 0 and ket 1 with alpha and beta as coefficients in the first system. The second system, let's assume that it says 0. So we want to copy this, and when we copy this, uh, how do you copy? We use usually some kind of a unitary transformation, because all transformation in quantum are unitary, and uh, uh, all the operations are always going to be tensor products. So what we do is we assume that, okay, let's have these two, and we'll have a unitary matrix. This is assumptions right now, okay? And then at the end output of that, what should we get? We want that it should be copied, so the 0 should become psi. That's simple proposition. We want to uh, say that cloning theorem can be proved right if this happens. So let's see how we can do it. So what we see is we have constructed a quantum circuit with a unitary transform, where we are saying that one qubit is at psi, one wire or one qubit is q0 at psi and q1 at 0, and then on the other side we want to see these two similar, because then only this has copied to this, and this is the box which does that. If that is the case, let's take a simple thing. Here you have a ket psi which is alpha 0 plus beta 1, alpha ket 0 plus beta ket 1, which is here, and we have a ket 0 which we are trying to do a what you call as tensor product, right? So if we do a tensor product, see that alpha 0, ket 0, and beta 1 and ket 0. So
Hello, Munir.
yeah,
Yes.
what's happening? Anything I am missing? Please.
Uh, what?
You are not able to see the share now? Do you want me to share again? Okay, I'll share again. Okay, here you go. Hopefully this time you're able to see, everybody is able to see now? Or is it some different complaint? I'm not sure. I think one of you may be able to handle it. If you have anything on the chat, you can put it. Oh, discard stuff. I think that somebody can take care. Maybe who is there? Okay, Thomas is there. Or somebody who has used it, Discord, you can just put the link to that. Let me move on to, without getting distracted, let me move on to my sharing. So my share where I had, okay, here. So what we are trying to do is we are trying to get, by having a combination through a, by having a operator, unitary operator on psi to copy and get a psi. So if I do a unitary transformation on this, which is the input, you are going to get a psi psi. That's the assumption. If you get psi psi, psi is nothing but alpha ket 0 plus beta ket 1, and another psi means it will be equal to alpha ket 0 plus beta psi. This is the assumption, right? If this is going to come, then we can multiply and get it as alpha square ket 0 0, alpha beta ket 0 1, and alpha beta ket 1 0, and beta square ket 1 1. This is, all assumption is alpha beta belong to complex space. We are not doing any unitary, we are just looking at the output what we want. So if this is the output we want, how is it going to come from this? So we are trying to now produce this from this. So if we try to produce from this, what we see is, if you have ket 0 0 and ket 1 0 and a unitary matrix, let's say, exists, and which is a, let's say, C naught gate, and if it is a C naught gate, ms bit, let's say that 0 0, and 1 0 are there. So 0 0 unitary transform is 0 0, and here it will be 1 1 because there is a bit flip. And therefore, if we apply this to alpha 0 0, which is what we saw, alpha beta 1 0, if we go through unitary transform, we will get an alpha of u ket 0 0 plus beta of u ket 1 0, which is now because of the transformation we are getting alpha 0 0 and beta ket 1 1. And if this is to be satisfying this, then either alpha is 1 or beta is 1. And in case alpha is 1 or beta is 1, that means the state has collapsed. So that means if alpha is 1, you get a result alpha square, which is 1, which is ket 0 0. Rest of them all will become 0. If beta is 1, then all this term will be 0, only we will get a beta ket 1 1. So we are not getting what we want. What do we want? We want psi, which is a combination of alpha ket 0 plus beta 1. We are not able to get that. What does that mean? It means that cloning is not possible. Simple proof. Assuming that it is possible, we have proved that it is not possible because it will collapse to one or the other, and we really can't get the combination that we are looking for, which is alpha 0 plus beta ket 1, alpha ket 0 plus beta ket 1. So what does it means is that you can have no circuit which will be able to clone it. So now the dilemma is, what do? We do want to communicate that if somebody called Alice has a let's say a state which is combination of the states, and to pass on to Bob, how do we handle that? So now let's think of this in a different way. Let's think of, because it is not possible to clone, we know, but can we somehow reach whereby some operation on either side can help them do what they want? Yes. So that is the term teleportation, and we'll using C naught we'll do it. And um, so here what's happening is Alice has a qubit psi, which is this combination, and wants to share that with Bob, who has got a qubit which is in zero state, ground state. So they have a, let's assume that they have a lab, they are in the lab, extended lab, and they are connected through a C naught gate. Let's say if that's the case, then uh, what Alice does is she operates a C naught. Um, that is, this is the MS bit, this is the LS bit. Remember, that is the difference here. So what we can do is, if we apply this with a combination, uh, she can do so by measuring in plus minus state. And if she gets a plus, then she tells Bob he doesn't have to do anything because he has got what he needs. Okay. But if she reports that it is a minus state, now plus and minus equal to what, that we have to see. Plus equal to 1 by root 2 of ket 0, alpha ket 0 plus beta ket 1. That we have done already. Uh, if you do a C naught, you will get that, and we'll see that. It's not that I'm just giving you at this time a result. So the simplest thing is apply a C naught, and you will get a combination alpha 0 0 and beta 1 1. This is nothing but a Bell state. Bell state is nothing. If you do this alpha 0 plus beta 1 0, because it is a C naught, this 0, this being 1, MS bit being 1, LS bit being 0, it gets transformed through C naught to this. Now, having this, you can bob in that case. So the original psi or the ket psi is alpha 0 plus beta 1. Bob is just entered into picture his lab, and they apply a C naught, Alice applies a C naught based on MS bit here being 1. So this is an exclusive OR, you can call unitary XOR or C naught, which is nothing but flipping the bit. So it flips the bit, and so this is an entangled state. This is maximally entangled. For a 2 qubit, if you have 0011, that is the maximally entangled state. There are 4 of them. You call it psi plus phi minus psi plus psi minus. So, but typically what we are trying to express is, if Bob can get this, he can resolve this. She can take a telephone call and tell Bob, hey, I am trying to, she measures, if she measures means she will destroy. Whenever anybody measures, they will collapse the state. So she will lose her alpha 0 plus beta 1 if she measures. And but Bob has already got this one. So if she says that by measuring, okay, she gets a plus, then Bob has nothing to do. Bob has already got what he needs, and he can just take it and he can get it a value out of it. If it's a plus, he'll get this. If it's a minus, then he has to flip. So if it is a minus, they have to flip. Now, this is the whole logic. But let's look at it in a way which is more easy to what you call understand. So let's say we have phi ket 0 beta 1, and if you do a measurement on this, you get a 0 with probability alpha square and 1 with probability beta square. That's the usual measurement on a CATSI if you do a measurement with a device. And let us call this device as device. It could be a Geiger counter, it could be a photon detector or whatever, depending on how the spins or photons or whatever your physical media, physical implementation of the state of the electron is there. If the device is N0, is in a state 0, then we call it N0. So needle on this will go to either position 0 or 1 depending on what is the collapsing to. If it collapses to 0, you get a N0. If it collapses to 1, you get a 1 N1. So basically what we are saying is, what does measurement mean here? Because at the end of the day, you are measuring something, and what is the measurement needs some device. Assume that you have a device which is, it could be one of the physical appliances which is either aligned with z axis, so we call it as z basis measurement. If it is aligned with x axis, we call it x basis measurement. Assuming that we have a needle with a measurement, and so this is equivalent of applying C naught gate between wire 1 and 2. Why this? Because if you have a wire 1 with alpha 0 plus and you apply a C naught, then you are getting this combination, which is a Bell state, right? Which is the maximally Bell state alpha 00 ket 1 plus beta 1 1. So when we do this, we can keep on doing this. This is 1 to 2. You can do 1 to 3, 2 to 4. If you have 2 qubit, then we can do, and then it will come out that if you have alpha 00 plus beta 1 1 for 2 wire, if you have now 4 wire, and if you are doing 1 to 3, so if you look here, this is the state. Because now what is happening is, um, you are having already 00 here and 00 here to start with. At this stage, you have got this one, this 2 is in this state, but these two are 00. So we are just adding in front because these are MS bits. So we are just adding 00 and then trying to figure out this 00, we add 00, that doesn't change. But the second one, if we try to change, it has a 1 1, so it has a 00, so this bit will flip. So by applying 1 to 3, the C naught, you are getting from 0000 plus 1110, because this bit is now getting flipped, which is nothing but this bit is getting flipped. Now same way, if you apply 2 to 4, then what happens? Then again, one more uh, operation happens, and that happens because this is a 1. So you have 0 0 remains as it is 0 0, and the beta 1 1 1, this being 1, now you are getting a flip on the, this is 3 to 4. So here we are applying here to here, and therefore that will flip one more bit, and so again you are getting a alpha 4. There is 2 qubit with a maximal entangle 0 0 0 0 1 1 1. This is called cat effect. And so you can keep on doing C naughts from n number of time, and you can keep on getting maximum state. This is not limited to just 2 qubits. It can be taken to the infinite, not infinity, rather than a finite number of states. Now, how many finite? Because this is micro, and subatomic particles are in certain state. Maybe this will be applicable for maybe 30, 40, 50, we don't know what, when it will collapse. The states are coherent and maintainable only for certain number of electrons. If it becomes 30, 40, 50, then it becomes more like a microscopic rather than a subatomic. If that happens, then it may collapse. So you may not get any of the states which are coherently available for you to measure. So it collapses in that case. That's why this is, it's not that you can keep on adding infinitely, because there is a noise element which, or whenever a qubit interacts with the environment, there is an impact on that, and that is the noise impact. And therefore it is very important that as long as you have a closed system of the qubits, you may not have the impact. But once you have um, more number, what number we don't know, but we can say 30, 40, 50, depending on how we are able to keep it close. The environment will impact. So what I have done is, this is called cat states. Like usually Schrodinger has a cat which is in a box, and if you have a, what you call, um some uh, some atomic, like uranium particle or something, and so it is causing, it may cause the radiation which may happen, that cat may die. But if it is inside the box, until you open, you won't know. So that is called as cat state, and that cat state is what. So you can think of in terms of either a wave or particle. Either way, the condition is not known. It's only probability is that it may be dead, it may be live. So that is called cat state. And also there are certain things important to note here. There can be a compute aspect of it, and there can be a communication aspect of it. There two are different in the sense that uh, channel, quantum channel, when we say, so we have a communication, we have a classic communication. So if this is a wire, this is classical communication. But then if it is, how is this getting entangled? It is doing through quantums. So these are qubits. So qubits, when they are local and when they are non-local, there is a difference. I won't get into Mars and Moon and all that, but just say local and non-local. So either you are in, suppose both Alice and Bob were in the same lab, that's a different story. If they are in different building in different labs, then they are non-local. Or it could be that they have a space station where there is a lab, and Bob may be there and Alice may be here. So that is local and non-local. So simple term we use without getting into too many details: local and non-local. And if it is local and non-local, and if cloning is not possible, how is that you are able to entangle, and if the entangle can be teleported? So the issue is, if that is happening, um, that is where we remember that you can go and look at the EPR, Einstein, Polosky, and Rosen, EPR. So EPR paradox is, they assume that, Einstein in 1935, along with these three people, they wrote a paper and said that quantum computing is incomplete because it cannot uh, tell if there is a state. They called it a spooky. That means if if Alice says something and she measures and it collapses to zero, then one Bob, even if he were in, let's say, moon, that will also become zero. Whenever he checks it, it will be in zero state. So what it means, it's a spooky, um, what you call state change or state collapse at a distance. How can it be faster than speed of light? That is one question. And how can it be not well explained by uh, quantum mechanics or quantum theory or quantum physics, that they therefore put a term called that there is a hidden variable. So there was a gentleman, this John Bell, 1965, he came up with theoretical explanation that, well, if that is the case, then we always talk about orthonormal basis, and so if you go on orthonormal basis, that means they are uh, either it can be 0 or it can be 1, not both, right? That's the orthonormality. And if you assume that they are not orthonormal, then you can go with not orthonormal, and then you can add them. And so the probability should, if you give zero point 0.5 is the probability for each of these 4 Bell states, then if you do a sum of that, it comes to 2. So the claim can be that it cannot be greater than 2. But then he proved that it is greater than 2 root 2. He came up with a number, and that means what? It is around 0.67, somewhere around that number for 4 of them. And so he proved, it went by the other way around. That is, there are no hidden variables because I can prove that it goes more than 2. And that was the way he proved. And these are, so there is a classical channel, there is a quantum channel. Quantum channel, if you think of, now, have you ever heard about quantum memory? No. Why? Because you hold the electron responsible for managing the state. And if it collapses, then you don't have the state. You have a collapsed state. So it is the electron or the photon, they themselves have the memory, or they are the memory. There is no separate memory. So they carry the state, and therefore you don't need a multitude of memory, as we had seen previously calculation, that you require a 4 byte per this one. So if you have 2 to the power n, and if I make that to be 100, then you have Yoda bytes of memory required. And who can produce Yoda bytes of memory? So that's why you maintain it in electron in the states as they are. So there are some archival, and talking about quantum channel. Quantum channel is the information theory. That is because the quantum mechanics was uh, conceived in 1935, and the information theory of Shannon, that was somewhere in the later stage in 1950s or something. So there was some 22-year gap between the two. So information theory and quantum theory were merged by later players like Feynman and others. So essentially what I want to say is there is a quantum information theory also, which is based on the probabilities. Most of these are, because everything is uh, indeterminate, and uh, and that is also, there is a uh, uncertainty when you measure. So all these decoherence is there, entanglement is there. So the aspects of, and not only that, it is unitary. So these all aspects put together, the two ways of looking at it is either you look through the framework of quantum channel having some memory to be able to, or persist, not persist, rather the probability which it carries because of entanglement. So entanglement becomes a kind of a communication, or you can call it as a computation holding in memory. So it becomes some kind of a vehicle for the entanglement to be transferred. So this is the cat state. More details are on the links, you can go and see. So I can here just put down, for the sake of simplified version, that if you have a Bell state, you have to create a Bell state. So that means if you have a pure state, alpha ket 0 plus beta ket 1 is nothing but a pure state, because you are able to separate the alpha 0 and beta 1 on collapsing. Either it will be a 0 or a 1 depending on the alpha beta probabilities. And but if you do a measurement, that means if you entangle them, then the entangled state is 1 by root 2 ket 0 0 plus 1 by root 2 ket 1. This is one of the best states. Okay, and there are four of them. We just say one of them we are using, 5 plus, let's say, or psi plus. I don't know which one is that, but anyway, we are using one of them. And what happens is, here when you do a C naught and measure, obviously the same thing is being expressed. The only thing is, this is a common channel, or in our book they call it as BB, because A and B, for here we are taking MSB first and LSB later. That's why it is Alice to Bob. In the other case, in the book, you will find the it's not the dot and the exclusive are here, it is the reverse. You have plus here and dot here. That's the reversal. And accordingly, they have the see the if I remember correctly, in the same thing happened in previously when we started in the computer science early. The Intel architecture was always a LSB first, whereas you go to PDP-11 and all others, they were always MSB first. So you go MSB to LSB, whereas you go LSB to MSB. So it's a convenience, and Qiskit unfortunately does LSB first, like Intel architecture, and therefore you'll find it reverse a bit confusing for one who has done MS bit to LS bit. So, but essentially they do the same thing, and that is control not. Whether you call exclusive or unitary exclusive or control not, it is like you control a NOT gate to flip it, or you use a exclusive OR, because exclusive OR is what, 0 0 0 0 1 1 1 1 1 1 1 0. So if you have two ones, then it will switch to 1 0. And same way, if you have 1 0, it will go to 0 1. So exclusive OR is nothing but the MS bit causing the flip on the target, or source bit flipping the target bit. Whether you do it in 2 qubit, or you do it in 4 qubit, or n qubit, doesn't matter. Even in 3 odd you can do it. It's all a matter of how you conceive. So assume Alice Bob are connected in their app from two separate locations. Both have an entangled qubit, which is plus or minus state. So we create the entanglement, and here is the entangled state, right? Now when you do a C naught and measure, that's what matters. So when you measure, so Alice can, so this is common to both of them. Alice can measure here and tell Bob that, hey, it's a 0, and he'll say, okay, I got what I want. Otherwise, if he gets a 1, then he will flip it, and that's what it is. So this is a way of putting in a simple version, that you can use a C naught and you can do infinite of C naughts to keep flipping or keep creating Bell states. And this, so that is why, if when we said that, oh, most of the states are Bell states, or most of the mixed states are, um, some of them are factorable, some are not factorable. So when we call singleton, it means it is not uh, what you call factorizable into the lower state components. So lower means what? C2, if you have a C4 and if you make a C2 of it, and if you can have a combination of pure two C2s, that's what it means. So that is what here. So when Alice tells Bob that 0, then he doesn't do anything. He just picks up whatever he has and he can move on. But if she says, no, I have a 1, he will take a flip. Flip means what? Minus 180 degree, basically. So there is pi radian. Pi radian is 180. So he'll take a z, which is nothing, flipping. And this will show, okay? It's not like this is not demonstrable. We have got kits to the IBM quiz kit to demonstrate it. Now, there is something to summarize, and I'll put it in a manner which is uh, a protocol. There is a protocol, we say, and this protocol is simple. That is, if you have Alice, and if she does a um, what you call the C naught on a, you get a combination, and then you can say that this is the lab split. This is Alice lab, this is Bob's lab. So they have some common uh, connectivity, whether you call it a quantum channel or whether you call it a classical channel. The information has to be exchanged between the two. Without that, that means what, they are from the same source. Simplest physics people explain that, hey, there is a source, and that source gives to Alice this, and then same thing is given to Bob, and so that means what, both of them are from the same source. Otherwise you cannot happen, because that means what, if they are from the same source, then they have the similar uh, what you call attributes, and therefore then there is no so if Alice applies a C naught, then the other, it's a spooky thing, right? So if Alice applies, then Bob's qubit also gets entangled. That's the basic philosophy here, or the this is by nature, okay? It's nothing to do with speed of light, or nothing to do with local, non-local. Everything is same, because they are coming from the same source. If they are not coming from source, then it's a different story, because they are not the same qubits then, okay? And so now you take a Hadamard, or before taking Hadamard, sorry, Bob will take a measure, and if it finds that this is going to give some value, because this is a obviously assumption that he has to invert. He has to invert only if and only if, okay? If it is turns out to be 1. If it is not 1, then he keeps moving. His psi is still as intact. So if this is not 1, this has no change. So this is same what Bob had in hand when he got it. Okay. So now you take Alice decides to take a Z basis to X basis. So she does a Hadamard and does the calculation or a measurement using the device to find that there is a, if there is 0, then don't care, but if it is a flip, then they have to apply a flip here to be able to. So Bob can apply either X or Z depending on he gets a 0 or a 1 depending on the telephone call. So this is same thing. The only thing here is addition of Hadamard. Why did you do Hadamard is the question. And so the Hadamard is to make plus minus basis and measure on the Z basis, because psi when you started it was a pure one, alpha 0 plus beta ket 1. The only uh, qubit that was impacted was this, not this. So here by doing a C naught you got a this, but here you just have alpha 0 plus beta ket 1. So you do have to do something, and that is what is a C naught application. That is what, sorry, that is what the Hadamard application. So again, this is very similar to that, and again measuring that ends up in a flip or no flip. Okay, so that's the representation of quantum teleportation summary. Now what we'll do is, this is further extended, that what happens in this mystery. So the only important thing to note is, whatever you do here, xz and all that, the two values you are communicating here, what happens, if you give a 0, that means you have given one information. If you have given another one, then it's a 1, then it's a flip. So what it means, you are essentially, the coefficient b1 and b2 which is required is what is expressed here. So essentially, if you have a 2 alpha and beta, you need to convey through classical communication the term alpha and beta, even though they are not identical. What I mean by electron, if I have electron, Alice has electron, Bob has electron, both have electron, but you are not copying electron here. You are just telling the other person, hey, this is the states of alpha and beta, and how do you express that? Through these circuits. So it is teleportation is nothing but communication of the coefficients without telling it is the coefficients through the circuit, and that's all it is. So we are not copying. So it's not identical electron, because if you look at electron of Alice and Bob, they are same. If they are from H2, they are from H2. Electron doesn't change anywhere. They are same, but they are not identical. They are similar. And you are only transferring the alpha beta, which are the variables, nothing else. And that is how you are able to do a complete communication through either classical or through quantum, whichever channel you want to. It's just, or you want to think in terms of computation, you are holding the value on the uh, BB, they call it. And there is a BB84 protocol. I think this name, I forget what of this. Some scientist who has come up with that protocol. This is a protocol. It's like we do a TCP/IP protocol or a some other protocol in communication. This is a protocol where you just say that you take the C naught and send one variable, take a Hadamard and send another variable, and the other end, whoever it is, Bob, can reconstruct what Alice says. Okay, that's the overall quantum teleportation. And so this is a transmission of the arbitrary states of, because we are not saying what is alpha and beta, we are just saying this is a ket 0 alpha 0 and ket 1 alpha beta 1. So it's a alpha ket 0 plus beta ket 1, which is arbitrary state. We have not said what is value of alpha beta irrespective of that, because it's a probability, it's a density matrix. So when you teleport the density matrix values through some B1, B2 kind of thing, which is nothing but a binary bit in this case. It's a 0 and a 1. So you are just doing a classical communication with B0 and B1, and it's equivalent of a quantum teleporting. So this is the essence of the mystery of conveying B1 and B2, which is nothing binary bits, and which is which is helping the non-local person to take their electron and impinge in them the necessary uh, alpha beta to be able to acquire the combination. So you can do a quantum teleportation using this. This is, I think, called BB84, if I'm not mistaken in physics term, but that's the protocol. So now we go into uh, running on IBM Qiskit. I think I have spent around 45 minutes roughly. Now let me go to the run on IBMQ. So before I run into the IBM what do you call Qiskit to show this, I'll just walk through it. That Bob and Alice, in this case, you have seen Alice is at the bottom because she's on the MS bit. Bob is on the LS bit. So this is reversed, and you saw that dot and cross which I have used, it's reversed. In fact, I'll show you in IBM, we will have to do it ourselves physically. I did not find a way to do it uh, this way. Okay, but that's how we have to do it. We have to be aware of what is MS bit and what is LS bit. And so if Alice has a state system or a state system A with alpha 0, ket 0 A and B1, it's just being uh, C naught or exclusive or unit it's called as um unity XOR gate in terms of our referred book, and they are taking the combination thereof and adding the two and projecting this is equal to the state. Okay, that means all it here boils down to A and B states being. So when you apply C naught gate or a unitary XOR gate, uh, you are entangling. And once you are entangling, then the next question is how do you measure it, right? Because you have to measure to know what it is. And that is where you do a plus minus basis measurement. Same thing what we did. So first is entangle, then measure by Alice on plus minus basis. Alice calls and shares the results, and the Bob acts on it, depending on if it's a 0 or a 1. The same thing is expressed here uh, nothing much new on this. It's a simple one. What we did, it's simply that the MS bit and LS bits are reversed. And this is step 1, 2, 3. There is a step way of doing this. So quantum teleportation algorithm for transforming quantum state from Alice to Bob, that is the one which is represented here. Now, this we will see by a run on IBMQ. And before I flip to IBMQ, just I want to show here just the difference, just mark the difference. Okay. Here we have got this way. That means the affected bit is here. This is the source bit. So this is the target bit. Whereas in this case, this is the source bit, this is the target bit. So affected is this one and based on this. And that's the reason when we go to IBM Qubit, IBM Qiskit, we'll have to do teleportation in this way. So here, just to keep the sanity, Q0, Q1, C0, C1, C2, these are all what you call as classical and quantum registers. The numbering is always perfect. That means MS bit to LS bit is what is the approach. So this is Q1, Q0. Next one will be Q2, Q3, Q4. So it will keep expanding on the register, the number of bits, and MS bit will keep increasing. So implementation wise, that is simpler. That is why most of the people, including Qiskit, IBM, I don't know any other, whether it is what you call Pennygate, what other tools are there, Q, what is called CU Quantum, which is the NVIDIA's. There are many of them. Okay, don't assume that IBM is the only one. There are plenty of Qiskits available in a different way. Some people use Python, some people use C++, like Intel uses C++. So they have got their own compilation, transpilation. For us, important as a starter, or at least at the introduction level, is to fundamentally clear what we are doing. So here, the only entanglement we are trying to do is again psi A and 0B. Why 0B? As I said, you start with a clean slate, right? When you have a register, you want to zero it and then before you copy. So even in teleporting, the same principle is applied. And using the C0, the application of their state is A and B are systems. So we know that we already have a formula where we said that if we have A, B, C, D, alpha, beta, gamma, delta, pi, nu, z, there are standard coefficients which we apply. And at some point, we don't even need this because we know that all this boils down to what? Having alpha 0, 0 plus beta 1, 1. Why beta 1, 1? That question we have answered already, that there is a flip because of beta 1. If this is the source, so beta 1 is the source in this case, so this will flip. So the 0 bit flip. So this is again a creation of nothing but build state. So without complicating further, we need to know that if we show this on the IBM Qiskit, we should be able to do it. And the same thing on IBM Q is here. Okay. So I will go into IBM Qiskit and then come back. Okay. So let me do one thing. Let me stop sharing and reshare. So stop sharing and then I will reshare to get you the screen which is getting started. I hope this is the one. Okay. So we are, no, not this one. Sorry. So I'll have to reshare. Okay. Stop sharing. And then I'll have to reshare given that I didn't share and screen. And I think I should. Okay. Now you're able to see the share. Hi, everyone. Can somebody
Not yet.
respond? Okay. Okay, good. So what I have done is, obviously I had my own, but since I wanted to make sure that what Google gave and what I have are similar. So
Sorry, the,
just to,
there is no share yet.
oh, there is no share? Oh gosh, I thought I shared. Okay. Select tab. Okay. Are you able to see now?
Okay, now it's on. Thank you.
Okay. Are you able to see the full picture?
Yeah.
Okay, good. So what I will do is I can just, before even doing, I'll just create a new file. So how do you do a composer? Use the composer. I am in the composer and I am just saying create a new file. So when I create a new file, I get default Q0, Q1, Q2, Q3, C1, C1, 2, 3, 4. Okay. Let's assume that I don't want so many. I just want, you can see, can you see the QASM on the other side? What I am trying to do something? I want only two of this and I want only
Yes.
two of this. So then what happens? I get Q0, Q1, C1, C2, right? So there are two qubits and there are two classical um, bits. Okay. So what I can do right now is just to show you simple thing how it works, because there are so many gates and it's complex. So what I'll do, I'll just put it in a, so you got, these are the operation. Okay. So what do you have? You have a Hadamard gate, you have got classical gates, NOT, CNOT, and then so you got Toffoli, swap, these are quantum, phase gates, TSZ, and then there are non-unitary like measuring, reset, control, conditional, and all that. And then there are other gates like SX and SXY. There are many gates, right? So all these are complex things. The simplest way to think of it is, if you have a qubit, what do you want to do? Okay. So based on what we saw, the simplest one, okay, nothing doing except for C naught, I don't want to do anything. Assume Q0, Q1 are there, which is there in the register. All I want to do is I want to create a C naught. So the first challenge you will find in C naught is there is you cannot just take a C naught and dump it, because if you dump it, then what you find here is not the C naught as described in our book, right? This is, we want the other way around. That is, we want this, which is MS bit, to apply on. MS bit is the source and 0 is the target. So what am I going to do? I don't know how to draw it. Okay, no problem. I'll make this Q1 and make this Q0 and then see what happens. So you got reversed. So without even understanding anything, I know that all I wanted was, our approach was, this is the Q bit, Q1, which is MS bit, and this is the LS bit as per the diagram in the book, right? And therefore I reversed it and I am got what I want. So now if I look at this, it says state 00, probability 100%. Okay, fine, no problem. Now let's say if this is not probabilities, I am looking at state vector. What does it tell me? It tells me that we are in the 0 state. Okay. Now if I say, okay, I want to inspect this and then say, let me run this. Step 1. So it has executed. So what has happened? If I look at it, it's in the state vector is in 0, 0. Probability is 100%. Okay. So this is one of the ways to do a C naught. Now, what happens if I want to do something like Hadamard? I'm just for the sake of it. Okay. I'm not trying to do anything very specific here. Just if I want a Hadamard, then okay, what do I want to do Hadamard? Where? Okay, I want to see the destination, right? Because this is the source, this is the destination. So if I put a Hadamard, what happens? I want to know. So I'm not able to put Hadamard because it is in run mode. So I have to remove out of run mode. So how do I remove out of run mode? It is here. Now if I drag and drop this Hadamard, it will be on the target. So now what happened? Because of the Hadamard, the target has now changed, right? You can see now it can be in the this state 0, 0 or 0, 1. How this happened? Because I dragged and dropped the Hadamard. So you can see that one of the qubits is now a combined That is, uh, it has got a combination. That means it is superposition, and it's a mixed state. And mixed state is showing as 0, 0 and 0, 1. Obviously, you can look at the state and look at the probability 50-50. So what it means is that by just dragging and dropping, you can create any circuit you want. If you don't want this, you can all put it into dustbin and get away with a new one. Okay. So it's not like, and plus, suppose I want to take this off. Okay. All I have to do is take this and just put it in, delete it. Now I can go ahead and add things. I don't want Q0, Q1 alone. I want one more. How do I add one more? So I'll go here and check here, and it says +1. So, okay, I'm going to add one. Same way I'm looking here. I will put a +1. So I got 3. So now you got 3 qubits, right? And to start with, it's in the 0 state. So if you look at the diagrams, what you have ms bit to control is ms to ls. So what the author of the prescribed book says is that he assumes that Q2 belongs to Alice. And so if Alice is the one who is going to handle, uh, how do you create a bit which is intermediate? I call it BB. So what I can do is I can take a, uh, first thing is I have to impact Q2, right? So what I am going to do is I am going to look at what gate I have got. I got C0. Okay. Take and drag and drop C0 here. If I do here, but this is not the way I want the reverse way. So I'm going to put this as Q2 and this as Q1. So I have reversed it. If I reversed it, then I get what I want. So this is the source bit, MS bit, affecting the target bit. And if I look at it, this is the state, and this is the probability, and state vector is showing this. So if I say, okay, let's see that we execute this, and okay, so we are in one way. So same way I'm going to take one more. Okay, this is just arbitrary because I know C0 very well. I'm going to add another C0 I'm going to drag and drop. Okay, so let's take C0. No, I cannot drag because it is in the inspect mode or run mode. It's non-run mode. Again, I can bring the C0, put it here. But I don't want this way. I want to reverse it. So I'm going to say Q1 should impact Q0. Okay, what do you expect of this? So if I run this, what should I get? If I say, sorry, inspect, right? So what is happening now? I look at the state vector and you are getting this impacting this impacting this. Okay. Now, this is what the implementation of C0, and this is, but none of the states has anything, correct? At this time, we are not seeing anything that is happening here. It's all 0, 0 state. Okay. But now if I put a Hadamard, let's say, I just want to stop this. Okay, and take a Hadamard and put it here to measure it. And or not even Hadamard. Let me not even put Hadamard. Let me take that off. Let me just measure it, right? We have no measurement till. So where is the measurement? So let's drag and drop the measurement here. Okay. If I do this, then what happens? Okay. If I take one more measurement, I want all three to be measured, let's say. So I'll take one more of measurements. Where is this? Measurements. Yeah, here it is. Okay. So I take one more measurement and put it here. Okay. And then now you got one more measurement, let's take. Where is the measurement again? Here it is. Okay. So I take this measurement and put one more. Okay. Sorry, it didn't go to measurement. Yeah, okay. Okay. So 0, 1, 2. Okay. So what I see is this is how one does the uh, working on the uh, measurements and trying to get a measurements of each one of them. And then so this goes to C0, this goes to C1, and the third one goes to, third one is not there. What happened? 0 to 0, 1 to 1, 2 to 2. Oh, there is only 2. Sorry, there is no third one. Okay. So, okay. So now you got the hang of what is to be done. Okay. Now exact what we are doing, I'll show you. Okay. Because I have done my exercise. Here is one exercise I have done. And here is another exercise I have done. So you can do many exercises. Let's go to uh, entanglement, and this is one of the combination. Okay. Now you can do many of these and you will come up with different numbers. So what I'll do is we know that we are measuring 2, right? Let's remove the measurements here. I'm showing by deleting. We can also show by adding. Let me just delete this. So I don't want this. So what I'm going to do, uh, delete this. Okay. No. Oh, it is in the run mode. You cannot delete in the run mode. So done. Done. Okay. Now you see what happened. So you remember that we had take a flip. If you take a Z, you get a flip. If you take a H, then you get a superposition. And so now at this state, what is this? You can see if I go by state vector, you are getting 0, 1 and 1, 1, 2 qubits, right? So one of them is in the 0, 0 state, another is 0, 1. So this is in 0, 0 state, this is in 0, 1 state. And we can measure it. That is how the measurement was there previously. You can also look at the probability and then you will see both of them being 50-50%, roughly 50%. Yeah, this is simulation, so you are getting 50-50 exact. So this is one of the ways. So I will go into now what Professor Gokhale had provided us for entanglement 1 and entanglement 2. So this is the exercise which he went through, and he had applied a C exclusive OR Q0, Q1. You can see this is the dot, this is the control to Q0 and a Hadamard and the measurement of that. And when you look at the measurement of it, that is 1. And the second one is Z. So if you remember, we had done Hadamard and Z. If you look at our earlier circuit, we were always doing Hadamard on the source and the flip on the Z, and to be able to come up with the combination so that Alice can give to Bob the states, and Bob can either measure or not measure. In this case, this is the measurement. Here, if we put a measurement, then we'll get which is the measurement here. So we are getting a state which is different. You can look at different places, different states will be there, and probability will be there. So if you look here, and then you can look at the measurements, and you can reset it, and you can rerun it. So basically, this is one of the states. So this is the BB84 protocol, or taking a C0 from source to target, taking a Hadamard, followed by a measurement, and calling, and the other one that is sending the bit 1 as 1, and the second one taking a flip of the gate on the destination and providing another bit. So you have got the 2 bits, and that is what is being used. And when it collapses, because you measure, you collapse, this is what you get. Otherwise, without measurement, if you hold, you will have the combination of what you need. You don't need this. That is the way it is. And the second one, I think before I go to second one, I need to go into the slides. So I will come back again here after I go through the slide. So you are better off understanding that uh, rather than, uh, yeah, okay, let me stop the share and reshare and share again this time. And I go to the slides. So I again go through this. Now you can see what we were expecting. In the simple case, it was just a Hadamard and measurement of 1, and let the LSB be left as it is, and we got this combination. Now let me go to the second one. Here we had done a Hadamard and Z, which is what we had done right now previously, right? So we took a Hadamard measure of 1, Z, and then so both of these combination are respectively presented in the step 1, step 2, step 3 manner. Step 1 is you do a entanglement, and then second you do the Hadamard on the what you call the source, and then you do a Z on the destination, and then measure in 1 and 2 and 3. And this combination, so when you do a Hadamard, you get a, when you do a C naught, you get a superposition. And you get a plus or a minus state. You do a Hadamard, you measure in a 0 1 basis after Hadamard. So because it is, now you will get a measurement. And so the probability is what is the density matrix that is shown up, and this is the state at the end of it, and this is what they have done, and this is the exercise they have left for us. So what I would say is take this and just drag and drop this on the thing and see that you will get a probability density matrix. This one, obviously, when you do a last measurement, it will collapse. So you are going to get one of the states. Until then, you may get what you call alpha beta combination of different values depending on uh, how the states are. So quantum teleportation, this is one of the exercises they have given. I'll leave it to you. But in the, so this was the part one, simple entanglement, and we'll go to another one. In this case, we are talking about the uh, steps as shown with a BB, which is nothing but a, in this case, they have put the Bob's lab here and Alice lab, because Alice, they want to make it in the MS bit and Bob in the LS bit. And this is the intermediate uh, states, which is sending, that means Bob creates something in the lab, which is nothing but a C naught. Hadamard is to create the entanglement. Once you create the entanglement, you do a C naught. So you get a Bell state, and that Bell state is what you transmit to the uh, what you call the Alice lab, and Alice has a access on that, and she does a C naught if required. Otherwise, she just takes as it is. So the arbitrary state which was there is conveyed and received and measured, and that way you are able to do a full version. And this is BB84 protocol, they call it. But this is simply just putting some intermediate step called 1A and 1B. Step 1A is here, and then step 1B is sent. So first is create, this is Bob's lab's creation, entangling Alice, and then sending, then Alice going and taking it off, either through the C naught or no C naught, depending on how she gets, depending on what happens previously. So this is before the C naught gate. Alice has a 3-qubit state system, which is, in this case, you can see here 1, 2, 3, 3 qubits, and 3 qubit states. What they are describing is you got a whatever the R at A had, and if you take a combination which is Bell state and do exclusive R, and then come up with numbers, something like what we do tensor product. So if you do tensor product, you get 4 values. So the 4 values are there, and those 4 values are again this time it is 3-bit, 3 qubit. So you are going to get 0 0 0 0 1 0 0 0 1. So these are all bit flips and all that, okay, standard as it is. I don't want to get into too much confusing here, just leave it. And so you will find this is what you got, and this is the, except for the flip, you can see there is nothing there fancy about it. If a 1 is there, it flips. If there is a 1 here, this flips. So this is MS bit being the origin and target being the lower LSB. So MS bit flips the target here, and same way MS bit flips the target here, and so you get this. So this is the full version, and we have seen this same thing. You are just going to step through the entanglement with, they call it as auxiliary or ancillary bit, which is just to, it's like our buffer we talk about. We have if you want to have A and B swap them, then you will have in between a C, which will be used as a swapping register. You bring A to C, then B to A, and then C to A. So something similar. This is of a auxiliary bit. The role of auxiliary bit is in, at the end of the day it has no meaning. That means it has a meaning only for swapping the register values, but at the end of the day you can discard it without any effect, because ultimately what one is looking for gets one. You can drop a qubit in between, you can have q2 to q0 and get the result, because base state is still a base state, right? Whether you put a q2 to q0 or q2 to q1 to q0, instead of having three zeros you will have two zeros, and instead of three ones you will have two ones. That's all. So this is quantum teleportation, and the same thing is being repeated. I don't want to too much repeat it. And the full version also, the only difference between the full version and the simple version is that you don't want to do if you have a 3-bit operation, and if you want to not use um, the what you call the vagaries, you want to have a identity matrix. So instead of saying that you have anything, wherever you do the operation you have identity, just add an identity without having any impact overall. At the end of it, it's just instead of having step 1 2 3, you have a step one way, 1A, where you are putting identity matrix. Now this is a short, right? So if you take 1 2 3 4, this is the depth: 1 2 3 4 5 6 7 8 9. So you got 9 and even measurement at 10. So this is like you create layers after layers and take a shot at it, but with the identity matrix to show that it is a 3-qubit operation. That's all. So you can see here, first one, this is going to impact this, but initially you need these two to impact this. So these two are together. Then again, here these three are together. Again, these three are there. So you want to have something, and when you want to measure this, you measure with two. So basically, you are changing the measurement from here to here to here. Three measurements you have made in between. So these are intermediate steps to just get the value as it moves from on the block sphere. Of course, you have to see on the block sphere. So I would advise that if you are seeing anything, you see on the block sphere what is happening. And we saw that in that one of them goes to two when it is a what you call superposition or entanglement, then you get the probability at two places on 2 qubits, or sometimes even 3 qubits. So all these are simple, straightforward implementation. Yeah, interpretation is more important. So, and there is a uh, swap. Now, what does a swap means? So before I go again to IBM uh, Quizzkit, I want to say about what is the interpretation of swapping. So swapping means what happens is if you have qubits and you got a 5-qubit machine, IBM Quizzkit is a 5-qubit simulator it gives you. So if you have 5-qubit maximum, you want to have 1 in 3 and 3 in 1 and interchange, that's a swap. So how do you do a swap? And if it is entangled, how do you swap? So this is entangled swapping. Because if you don't have entanglement, what you do swap is different, because you are if you try to do any measurement, you will kill it. That means you'll collapse it. But if you do an entangled swapping, then it will not get killed. Basically, you are able to maintain the state and yet move the entanglement from one to another. So you can move non-local to local. That means even I can sit here in my lab, and if there is a lab on the moon, I can swap it. So you can do an entangled swapping. And here, to complicate it, if I don't have any ice, then it is simple. All I take a Q1 Hadamard, and after Hadamard, that means what? By taking Hadamard, I have changed zero, it is ground zero state to Hadamard, means it is becoming, it is a what you call Hadamard, you are taking a plus, it will become. So once it is a plus and then this is the target. So now you got combination of 1 by root 2 ket 0 0 plus ket 0 plus 1 by root 2 ket 1, which is q2. And now you are impacting c naught you are carrying out on 1. Essentially you are trying to combine the two to create the Bell state. So you get a Bell state out of this. So when you get a Q1, Q2 build state, again you are doing a third to second to first one, a C naught. So every C naught adds nothing but one more zero, that is MS bit is added now. So if it is 0011 build state with 1 by root 2 alpha beta, then it will become 000 111 alpha beta. That's all it will become. And that's what you can measure here. You can measure here, check what is that, again do a CNAR. And so these are step 1b, step 2. All you are confirming every stage that you already have a state which is Bell state, and then you are trying to implement the Bell state is transferred from one to another to final state, where the in the step 3 the person who receives can actually look at it whether it is a swapped or not, and they can confirm. So it's just a um, it's a repetition of what we did earlier, just to make sure that swapping is also uh, carried out using quantum teleportation. So these are some of the major things we can go through it. I would say, without getting too much confused, just focus on the uh, what's the interpretation. And then obviously here is one of the entangled swapping using matrix multiplication the book has shown. So what he is calling UXOR. So Hadamard and identity matrix, which is Hadamard is 0 sorry 1 1 1 0 0 minus 1, that is the Hadamard, and identity is 1 1 1 1, right? So you got sorry, identity is 1001. So he's taking these two and then doing a 1 by root 2 of that. That is what you get from here. And this is the 4 by 4, that is for a 2 qubit, the matrix, the operator. So he is taking the operator, which is the UXOR operator. Here you can see the flip is at the third and the fourth, and then he is multiplying this, and then multiplying sorry, not multiplying, tensor operation. He's doing a tensor operation with respect to 0 0, and that is 2 qubits, and that is, it is at 0 state, so it is 1000. And when you apply 100, take all these, and ultimately you will end up with the two ones and two zeros in between, and this is nothing but 1 by root 2 ket 00 plus. So essentially here what he is trying to say is, here I have two systems A, B, and now I have a system C2. That means I am having A, B, and C, and then I am trying to take intermediate BB as my role to transfer. And if I do the UXOR of, that is I is identity matrix raised to XOR square, and Hadamard of the XOR of. So basically what he is trying to do is he is doing some 3 times C naught on individual, and this is a 4 qubit system, and therefore the matrix will be 16 by 16. So to simplify, he doesn't want to show all the 16. He's only showing the ones which are in the lower end of it, because at the end of it, he's calling CS Carlos. So he's bringing Alice, Bob, and Carlos, and then they are trying to Carlos and Alice qubits are entangled, as whenever Carlos measures 0 or 1, Alice qubit will collapse to 0 or 1. So essentially what he is trying to do is, you can bring anybody, A, B, C, D, anybody, it doesn't matter. At the end of the day, you have to keep on doing C naught, C naught, Hadamard C naught, and measurement. If you want, you have to do a flip with Z. That's all the tricks of this trade. And this is unitary, so you can use matrix to understand it, but it is much easier to do with the ket notation. So I would suggest that we keep to kit notation for all these rather than trying to do with matrix, which we have struggled, we have seen, because you have to get the trace of the matrix, and then trace defines the energy, and then you have to go with the density matrix to measure the probability. If you don't want that, um, then it's a difference. If you want it, yes, please go ahead. Welcome to understand that. But I would say the simplest one will be to use a kit notation to get over. So what is the implication of entanglement swapping? That is, you entangle two qubits that are far apart from each other. In this case, what he had done is Alice and Carlos qubits may both be on the earth, and we can entangle easily in the lab. With entangled swapping, we can then entangle Carlos with Bob's, which may be on the Mars. So basically, all you are trying to do is, if you go to my earliest ones, I will put it, this is the one you need to follow more than anything else. This one. So when you measure, all you do is C naught, C naught. Simply C naught alone is enough to get you all the states. All the this Hadamard and measurements are simply to get the values. But if you have a entangled, if you want to just have entangled Bell state, you can just use one Hadamard and rest of it is all C naught, C naught, C naught. So the only thing you need to remember is, if you have a pure state you want to mix, yes, welcome, use the Hadamard to get a superposition. But after that, you can keep on using that with a C naught, C naught, C naught, 1 to 2, 2 to 4, 2 to 6. You can infinity, okay? So you can have a 0, 0, 0, 0, 100 and 1, 1, 1, 100. That's a maximally entangled. That's what it will turn out to. And that's why the cat state is the important thing to understand. Either you express in terms of quantum channel, or you express in terms of hold up through a BB84 or whatever the BB they call it in physics. That is what it is. It's a protocol, and all protocol lead you to the same result. It's simply that you keep on doing exercises in different ways and ultimately come to the same result. So this is what I was trying to refer to. Here he is asking us to simulate the result, and those who are interested in learning the quiz kit, please do go through the exercise, because this is the one which simulates the result for entangling the qubits, and you can see that your collapsed state, and you can have the measurement for different combination. And this can be 8, this can be 16, this can be you can call it ABCD, or you can forget about ABCD, just use 0001. We understand that position, it can be A, B, C, D, E, F, G, H, etc. Okay, so Alice, Bob, Carlos, Dan, it can be anybody, it doesn't matter to us. So that brings us to almost end of it. 5 minutes are there. I'll just go once more back to the quiz kit, so that I'll stop sharing and show you the quiz kit once more. And stop sharing here, and then share again. Share screen. Go back to, sorry, I didn't go back to right quiz kit. So maybe I'll again do it. Stop share and reshare. Stop share. Oh, share is there. Share, entangle to bit quantum. Okay. So now you can see this is what, and all these exercises we have tried. Gokhale has tried his way of doing things, and I have tried my way of doing things. And this is on a composer. You really don't need to write code to do this. You can use the composer and see, example, simple one like we did in the earliest part today. First one I took was, did a reverse of it and then took a Z and a H, and that gives you the state. And this is probabilities, and so this is the way to go about. I don't know, I will leave you with the question. We have a few more minutes. At this time I will open the questions floor to the questions and answer. And This can be of any depth, you can do it. But this simulation is limited to 5 qubits. If you want more qubits, you will have to probably check that out. And there is one more thing which I want to say. The This is all based on Quasm, which is 2.0. Okay. There is one more Quasm 3.0, which is the recent one, where they have started experimenting in cutting the wire. Okay, what is it, cutting the wire? If you have a gate and if you cut wire, then what will it have show? That is one. The other one they are trying to do is, if I cut the gate, what happens? So cutting the gate, cutting the wire, these are the new uh, development which are happening and being present in Quasm 3. Most of the quiz kits from different vendors are only Quasm 2 compliant, and they do convert to their own language, not Python necessarily. Like if Intel is doing, they will do CPP, which is parallel C++, which is what their x86 is based on. And if you go to Quantum, which is the uh, NVIDIA's one, they have their own way of depending on ARM uh, um, codes. So they want to convert into ARM to be able to implement. So there are variations, calling, compiling, transpiling, interpreting, and each one has its own interpretation. In your Those who have computer science background understand it, but otherwise, if you are simply trying to do a physics like thing, then you can just go ahead and use the composer. This is simpler. Even Quizkit from Google is available, and this is because you get everything in the what you call notebook, and that notebook which IBM provides has got a library inbuilt, so you don't have to worry about the versions and all. That's the reason we chose easier to explain and implement. I think I'll stop here and ask uh, people to ask questions at this stage. Yeah, go ahead. It's open. I'm still recording. You can go ahead and ask questions. Anyone? Anything? Please feel free. No. We have got
Hi,
all this. Yeah, go ahead.
it's Thomas here. The the thing about the quantum memory, but there was some initial research about the quantum memory in the Caltech also
Mhm.
about this technology. I could send a email
Yeah,
question
I would
about that.
definitely like to look at it. It's not that quantum memory doesn't exist. It simply is that it is uh, it's still in the development stage.
Early
And
stages. Okay, yeah.
yeah, because I spoke to one of the professors from MIT. He told me that, do you know of anything quantum memory? I said, I don't know. I am myself looking. He said, that's why we are keeping everything in the electron. I said, okay. Then I did read a couple of things, but I could not figure out what that means. But my understanding is very clear at this time. How can you have, it's like freezing the state, right? At the end of the day, you want the register is nothing but you can't clone, but you want to freeze the states. And if you want to freeze the states and reuse it, and if it is kept in electron, it is much, the memory requirement is very low. But
Okay, yeah.
you cannot have the state, what you call, there are other gates that are being proposed, but I have no clue. Okay, I'm as much novice as uh, the professor at MIT who told me.
That's
Yeah,
right. Yeah.
Thomas, welcome. You give me the link and you can send it. And you saw that EPR explanation I have already filed in. You asked for that. I have put it in the uh, YouTube as well to see that if you go through.
Yes.
The only thing is that maybe I would have put it as probability. It is not the probability, because probability, what happens, you cannot have more than one. But if you do a non-commute, they call it commutative and non-commutative. If it is non-commutative, then you add, then you get some of the probabilities of 4 events greater than 2 point something, and that is what the joint, it's not joint but it's a sum. And so 2 root 2 is what Bell had claimed will prove that if you get 0.7, 0.7, 0.7 4 times, that is 2.8. So they take an average and that is 0.7, it is not 0.5. And so his proof is that, hey, you said that you can't go more than 2 for non-commutative, but it does go. That's how he proved. And other people have proved. Essentially, that is the proof. And that I have recorded part 2 where we had missed in the previously in the 7. So session 7 has got the definition of EPR clearly stated. Yeah, go ahead. Anyone else? Any questions? And if there is any
Are there
corrections, please
any
advise. Yeah, go ahead.
are there any previous like recordings of the previous meeting?
Oh yeah. We got okay. YouTube has got a channel which you can, and it has got 1, 2. This is the session number 11. So we had 11 sessions today, and next session we will be conducting on algorithms, and that will be the start of algorithms. Till now, we have been more focused on uh, quantum communication, previously quantum fundamental, and that is gates and communication. So there are YouTube. I think YouTube. There is a YouTube. I think it is. Let me just get you the link and put it here. You can take that. YouTube. Yeah, it is called. Yeah, this is the. I'll put the list here so that you can use it. One sec here. Sorry, here. Yeah, here is the. So what you can do is you can go to this YouTube playlist uh, at OpenTech Forum 1140 slash playlist. There are playlists in that. If you go to the OTF.quantum playlist, I think it is OTF.quantum is the list. You have all the uh, things there. I can probably click on it and show you right now. So I can share that and show you that it is there. Share and then share the screen. I hope this is the one or this is the one. I don't know which one. Okay, maybe this is the one. Yeah, you can see here OTF quantum, play all. And so, sorry. There are many. You can see here all in entire. So we have got around 11, I think. 101 starts with this. And the one I was referring to is 7th. The one which I discussed latest one. Yeah, go ahead. Yeah. Yeah. Okay. I think I'll stop. Yeah, that was the one I was referring to. I hope that gives you the idea what I was trying to tell. So you have all the sessions and even the IBM sessions. Okay, I have to do one of the things which IBM QuizKit, whatever explanation Gokhale has given, I have to create a file out of it. Okay, I will see how I can create a file because the link is there with me, but does anybody know how to create a session output of that? Um, I can do one thing. Let me just share screen and show you the yeah, okay, let me share this. Okay, so who is the so this is Gokhale's. Okay, so I have one my own, but let me take. So Gokhale ran 1 day ago. So let's say if I have this, can I have a file, save, view, make a copy? Can I make a copy, a share, make a copy? Let's say. Yeah, it is there, but how do I share? So let me do, See, this is where I have to ask him, how do I share this? I'm not aware of it, but I know that we can create a phase disk alignment reset file. If I do export, yeah, I think I can do export. Export. So you do a SVG. No, I want the entire thing, right? Choose the setting below. Okay, I want uh, white on black. No wrap. What is wrap? I don't know. So anyway, so what I'll do is wrap and no wrap. Okay, let me export it. Let's see what does it do. Okay, show in the folder. Okay. So composer. So what I'm seeing is it just gives the circuit. It doesn't give the code. I need the code, right? So I think I'll figure out a way how to get the code. But essentially, we can give the code to you, and there will be a Jupyter notebook. Basically, it means. So what I'll do is I'll preserve the Jupyter notebook where the problems are resolved for various sessions, and this session number, this is 11. So session 10 will contain that. So easy to remember. Session 10, I load into session 10 uh, uh, whatever the codes are there, so that you can pick up the codes from session 10. Session 11 is more to do with the entanglement. And then also one more, if you have any extra information you need, you can look into session 11. Having fun with block sphere, I have put a separate, that is not a video, but that's just a presentation. There we have spoken about all the universal gate. The Polis gates are not the universal gate. They are the gates which fold into themselves. That is, they are rotational. So if you take a XY, you can get a Z. If you get a ZY, you can get X, etc., etc. So they fold into each other. But you need additional one gate, and that is called as T gate, or no, not T gate. Yeah. So Clifford plus T gate is required. T is nothing but quarter gate. That means there are called a, so S square equal to X square equal to something, and they are all gates which are quarter turn, half turn, 1/8 turn. So 1/8 turn is the one which is required, so that you don't fold into itself but do something different. And therefore all the gates which are based on poly, either 2 qubit, 3 qubit, n qubit, they're all classified under Clifford gate. And there is a Toffoli gate which Professor Gokhale had discussed already, that is CC naught gate. Not just C naught, but C of C naught. And that is double complementing, that is, and with a exclusive R, and that combination. So that Clifford plus T gate is what is makes the things happen. And I can just show you the share before I close, so that those who are interested in further reading on the what do you call the stuff, I can ask them. Okay, so I have here. Okay, so you can see here the sorry, yeah. So this is session references. So under session references, what I have, I was trying to do in the session number 7, 8, 9, 10. So today's is 11. So I will load into this. So you can see quantum gate geometry. Are you able to see this? Can you see the title called quantum gate geometry?
Okay, yes.
This is the one which has got all the gates. So if you are interested in more deep depth into the, this is there, you can go through that. Current today's session was based on this QCF 101 P2 S11 P1P2. And this one I had prepared so that if anybody is really interested in deep diving into it, you can go into the slides, and that will give you much more information why the and that's the complexity. So your what you call the block sphere is not real. What I mean, block sphere is just a coincidence that accident that it can explain the vector of 2 qubit, but it's not really meant for that. It can do for 1, it can do for 2. So for understanding sake, you can do it. But actually, when you do m and n qubits, circuits and all that, you better off by doing with Dirac notation. Of course, after putting the Dirac notation, you can generate a circuit in the through drag drop composer, or could be with the Python code or whatever libraries you use, using the APIs that are available for um, Quantum Qiskit from different vendors. Obviously, the provider in the case of IBM Qiskit prefers that you use IBM API, but that's not the necessity. You can use anybody's API, including the Penny Lane, or there are others, okay, which are used in the Amazon and all that. So Zandu, and there are many players, okay. So it's not the end of the world that IBM is, but IBM is ahead in the game, that one has to acknowledge. And plus they are more liberal in the sense providing you information. And so those who are interested in quantum gate geometry can look into this. So with that session level, we'll be completing the gate circuit. And if there is anything, we can go into the whatever that cost, what is it? Disk, I forget the name of it, which Silicon Valley quantum computing folks have provided us, Disco or something, right? And I will try to log into that. And but if you answer each other, that is also good for us. If not, then I will ask what is his name? I think one of our colleagues was there who is helping us, and so I can ask him to provide. And obviously, there are experts in this group who themselves can answer a lot of things. And we have had something like 40 people or so who have been active in this. So we may not find them all the time because they go through the recordings and use it. So, but they will be active, and then you can get them, or you can send the mail and we will answer that. Okay. I think with that, I will close the call today, unless anybody has anything. Last call. Anybody, any questions? Dave? Okay. I think with that, I will wind up today and I stop the recording.